Okay, for lesson 3.4, we should be able to use limits to classify asymptotes. But what we need to keep in mind is that we also have maybe more efficient skills for identifying asymptotes for functions. So this is a skill we should be able to do with limits. It's, I suppose, how you would program a computer to find an asymptote. But it's probably not a method that we're going to find ourselves doing. First, let's review a couple of our limit definitions. Other than the properties, we actually had a couple of specific limit definitions. It was really important we understood that the limit as x approaches a of x was a, and that the limit as x approaches a of some constant was a constant. When we were showing all of our steps and limit properties earlier in the course, we're using the fact that the limit of a sum was a sum of a limit and constant multiples and stuff like that. But we were really trying to break down to these two definitions here, that a constant function is always constant, and that for a linear function, the value of the output is going to be approaching the value of the input. To deal with asymptotes through limits, there's a few new definitions that we need to tackle. And they are that the behavior as x grows without bound of x is, we'll just use this symbol right here. Now this isn't a limit because x is not converging towards a real number, and the limit itself, the output, is not converging towards a real number, but it is a behavior. It basically just says, as x grows without bound, the expression x will grow without bound. This right here is technically not a real limit either, because again, still x is not approaching a finite number, but we can substitute in a finite number here. If we see an expression, the reciprocal of x, as x grows without bound, you don't really have to memorize this. You can figure this out on your own. What happens when you divide larger and larger values? Well, your outputs will get smaller, but not smaller like -1 and -10 and -100. Your outputs are going to converge on 0. Okay. One last one is that the limit as x approaches 0 of the reciprocal of x. This one, I guess we need to have as a sided behavior. We would use that symbol right there. And we could use this to analyze behaviors around vertical asymptotes, but I don't think I'm going to bother much with that here. Okay, so let's say identify the horizontal asymptote. For f of x equals 3x minus 2 divided by x plus 1 using a limit. And even these directions aren't something that I plan on doing. I'll show you at the end of this question a quiz or a test level question that I'd expect you to be able to read and interpret, because an advanced function student should be able to look at this and give me, they may not be 100% sure, because some weird things can happen with rational functions, but they should be able to give me their anticipated equation for the horizontal asymptote. Okay. So using a limit, what we want to do, what a horizontal asymptote is really an end behavior. So we want to describe the end behavior of this relationship here. And I'm going to concentrate just on the right-hand end behavior. All of these definitions could be replaced with the left-hand end behavior as well, but I'm not worried about that. So we get a little bit of limit practice here. I suppose one other thing that we should review is that our limit of a quotient is equal to the quotient of a limit only if those two limits exist. This is the reason why we can't really treat infinity like a number. I can't say that, oh, my numerator grows without bound, my denominator grows without bound. This is infinity over infinity, and infinity divided by infinity is 1. There were many false statements in that sentence. So what we need to do is kind of like how we got out of an indeterminate form. I would say this is in a different type of indeterminate form. We've had indeterminate forms in the format of 0 over 0. when we were working with polynomial limits. Now we have another indeterminate form in the format of infinity divided by infinity, which this expression, this limit may exist, it may not exist, it may converge towards a finite number, it might diverge towards positive infinity. We cannot determine it from one of these formats. So we're going to manipulate this expression algebraically, not by rationalizing, not by clearing denominators, but by manipulating it in a different way to try to get one of these new definitions. And there's a couple of approaches that you can do. One approach is to remove the leading term as a factor. I'll try that first. So what I'm going to do, sorry, that's in the numerator and the denominator, is in my numerator, I'm going to remove a factor of 3x forcibly, right? Leaving me with 1 minus 2 divided by 3x. In the denominator, I'll remove a factor of x, leaving me with 1 plus 1 divided by x. Okay. Let's see, x divided by x will be 1, as long as x isn't 0, and I'm not worried about x being 0. So I'll get 3 times 1 minus 2 divided by 3x all over 1 plus 1 divided by x. And now you can show as many steps as you want here. You could show all of your limits properties if you like. We could use constant multiple and say this is going to be equal to 3 multiplied by the limit as x grows without bound of 1 minus 2 over 3x divided by 1 plus 1 over x. Notice that, sorry about the brackets, notice that now the limit of the numerator exists, and the limit of the denominator exists. So I can use quotient, limit of a quotient rule. There's the limit of the numerator, here's the limit of the denominator. I think I might stop here with the properties. I could use limit of a sum, constant multiple, limit of a quotient, but notice what's happening here. In the numerator, 1 stays constant at 1, and 2/3 x. You know what, I probably should show another step so that I can show you the definition. I will have 1 minus 2/3 multiplied by the limit as x grows without bound of the reciprocal of x all over 1 plus, I guess it'll be 1 times the limit as x grows without bound of the reciprocal of x. And there's one of my new definitions. We say that as x grows without bound, the limiting behavior of the reciprocal of x is going to be 0. So I get 3 multiplied by 1 minus 2/3 times 0 divided by 1 plus 0. And it is a very, very long way of figuring out that as x grows without bound, my outputs of my function are going to converge on 3. I would then interpret this statement, the fact that the limit as x grows without bound of f of x is 3, as meaning that I have a horizontal asymptote of y equals 3. Okay. The second strategy involves multiplying by 1 in the format of the highest power of, the reciprocal of the highest power of x in your numerator and your denominator to make sure that you get 1. So let's jump to the limit as x grows without bound of 3x minus 2 all over x plus 1. And we'll get, I'm going to multiply by the reciprocal of x over the reciprocal of x. So I'm multiplying by 1. As long as x isn't 0, I'm allowed to do that. I'm not worried about x being 0 because I'm studying what happens as x grows without bound. And I'm doing this inside the limit of. This gives me the limit as x grows without bound of, that'll become 3. This will become 2 divided by x. This will become 1. This will become 1 divided by x. A little bit faster and maybe more intuitive than the last approach. It should feel more like something that we've done in the past. It does kind of feel like I'm unsimplifying things, though. But a lot of the manipulation that we did in order to be able to evaluate limits, we weren't really making things simpler. We were just trying to get them out of an indeterminate form. Notice that the limit of the numerator, that stays constant at 3. That's going to approach 0. So my numerator is going to converge on 3. My denominator, that grows without bound. That's going to approach 0. This approaches 1. So my denominator approaches 1. In the middle of a curve sketch, I would not expect you to have to use limits to determine this information. I would hope that by looking at this expression, you could tell me it's going to have a horizontal asymptote of y equals 3. But again, you should be able to read this statement. If I tell you this statement, you should be able to tell me this fact. It would work well as a multiple choice question on an exam, for example. Okay. There on the rest of the lesson, you can see some examples of trying to deal with division form or classifying oblique asymptotes. But again, keep in mind this is just another way that we should be able to evaluate or determine these asymptotes, and it's probably not the way that you will be asked to find this information in a quiz or on a test. You guys okay? I just got a message from your teacher, Tegan, about a issue with the boom card. Oh, no. We got it.
I have to go to the presentation.
Okay.
Tegan's going to start working on her post. Can you listen to Martin?
Yep.
She's done her science stuff for tomorrow. We did 3 energy chains before that. Bart. No, we didn't do the bird one.
Bart. Bart.
We wanted to do the bird one, but then we realized it was the example that she gave, so I wanted to do that, right?
What did you do?
Tegan's bread. Rain. Sun. What was the second one?
That was the last
That
one.
was the last one.
The first one.
Oh no.